first part, excuse me, chapter 1, actually is to try to kind of give you an overall view of the universe. Remember, we talked about our cosmic address, right? Our sun is just one of 100 billion stars that are in the Milky Way galaxy, and there are 100 billion galaxies in the observable universe. So when it comes to our cosmic address, you know, the tightest is that the Earth orbits the sun, that sort of thing. But honestly, this is to try to kind of give you a sense for what is the distance, well, actually size and distance. Let's look at this up here. Do you guys see these cute little kind of a quartet there? Okay, these actually are all the terrestrial planets, rocky planets. Okay, and then we have the big gas giants. And then we have Pluto. Actually, we have Pluto and Eris, and that's kind of how they are kind of close to the sun and getting farther out. And with regard to size, that's kind of what we have going on. Pluto looks even smaller than Mercury, and it is. So with regard to distance, and actually there's a reason for this, if you start here, there's the sun. Notice we have our terrestrial planets nice and tight, okay? And then we have our gas giants way spread out. So that's on purpose too. We are in, I think it's in Unit 2 in here, going to talk about how our solar system formed, and this all kind of makes sense. We have to explain this in our theory of how the solar system formed. We have to explain our observations. So that kind of gives you an idea. I don't know if y'all have been to Washington, D.C. I've been there just a few times casually. And actually, if you go there, they have, and you can see them online, it's called the Voyage model. And they actually have like a podium. Here's the sun, and here is Mercury, you know, Venus, you know, Earth, Mars, and then you have to walk away far away, you know, to get to the gas giants. So that's kind of putting it into scale. So another way to kind of put our cosmic address into scale is we said that our sun is just a member of the Milky Way galaxy. Okay, and as it turns out, there are, I think I said a minute ago, 100 billion stars in the Milky Way galaxy. It's a beautiful thing, right? The closest star is 4.4 light years away. I think we talked about what does a light year mean the other day. And this down here is trying to show you where that closest star is. That closest star, 4.4 light years away, actually is in a constellation we don't get to see. Okay, you'd have to go, on my bucket list is to go to Australia. So go to Australia, you can see it. Okay. By the way, constellation, so the constellation is Centaurus. Okay. And then what they do is they take the brightest star and they call it alpha. This is usually what they do. They take the next brightest star, beta, okay, the next brightest star, gamma, etc. That's kind of what they do within a constellation. So Alpha Centauri is right there. By the way, in Chapter 2, we're going to be talking a little bit about Southern Hemisphere stars in Chapter 2. And we're going to see that, you know, how do I say this? Did I tell you that that's Polaris? For the semester? Okay, good. So that's Polaris, that's the North Pole star. But if you're in the Southern Hemisphere, you cannot see that star, obviously, if you're in the Southern Hemisphere. So instead, what you do is you use this constellation. There is no pole star for the Southern Hemisphere. You use this constellation, kind of go, I think it's like 3 lengths in, and right, maybe it's this way. But you use this to find the South Pole region. There's no South Pole star. So then our cosmic address said, okay, Milky Way galaxy, right? Big deal, and it is a big deal. But the Milky Way galaxy is just part of a local cluster of galaxies. Andromeda is another member of the local cluster. And bottom line is if you look around, there are 100 billion galaxies in our observable universe. And it was kind of fun because we talked about the cosmological horizon. And why is it that you can't see something that's 16 billion light years away? Well, the universe isn't that old, so our observable universe. So one last thing, okay, see this cute little boy playing on the sand, And so the slide says that if you were to take all the grains of sand that are on the Earth's surface, that would be about the same number of stars there are in our observable universe. So each grain of sand is a star. Like, really? I know, that's a lot of stars. Reminds me of Men in Black, where that little cat was wearing the little, yeah, Ryan, yeah. Thank you. That's kind of putting it in perspective. Okay, so I think you guys might have a question on your homework that says something about why do we say we are made of star stuff? And that's actually kind of a famous phrase of Carl Sagan. Did I already ask you this? Anybody know who Carl Sagan is? Neil deGrasse Tyson, I think I already did ask this question. I got the same blank looks. But Neil deGrasse Tyson is a contemporary of Carl Sagan. And what they do is just try to get people excited about astronomy, like we need a reason, right? But when we say that we're made of star stuff, what we're talking about is galactic recycling. And you guys know when you recycle something, basically, for instance, if you take your bottle, your plastic, and you give it to the recyclers, they're going to turn it into something else. Okay, so what galactic recycling does is count on the fact that stars live their lives, die, and they give their stuff back for new stars to be born. That's it. That's galactic recycling. And it's kind of being shown here in this figure down here. So we have within a galaxy, we have stars doing this. Okay, so this actually, I'm going to call this a protostar, like a prototype. Does it seem like it's not quite a star yet? That is, it's a protostar. And it can take like 100 million years for basically, let me go ahead and kind of do this too. Can you guys kind of see this stuff around, kind of swirling around the jets like that? Okay, that stuff right there is just what we call nebula. And I think I already introduced you to what nebula is. Okay, they can have different sizes of nebula, but basically it's a place there in outer space where there's gas and atoms and maybe molecules and dust particles. So that nebula actually came from another star, probably. Unless it's right after the Big Bang, and then it's fresh. But a star begins its life in a nebula. Okay, this actually would be probably, well, this is a live star right here. The second one, the star is alive. Okay, this actually is the later stages of the star's life. This third one right here, I'm just going to go ahead and say, sad face, the star is dying. Okay, the star is dying right there. Now, I think it's so exciting that the way stars end their lives, it varies, right? It mostly varies just by nature of how much mass they had to start out with. Okay, but it's dying, and actually, can you see the material that's kind of sloughing off? That's more nebula. It's getting back for more stars to be born. Galactic recycling. So here's the deal, and this slide kind of explains it. The time of the Big Bang, about 13.6 billion years ago, when our space and time and matter all unfolded, again, there's a little bit of discussion going on what happened at the very, 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 very first tiny seconds, okay? But the matter that we had, if we look at the periodic table, you guys, I know this is chemistry, right? But the periodic table, some of you guys know, is kind of arranged. So each box is an element. Okay, and can you see the number 1, and then you have to go over here to helium to find 2, and then you go over here to lithium to find 3, beryllium to find 4, and then you kind of hop across, and like you can see things like, what's the symbol for, well, like AU is gold, okay, see AU down here, it's number 79, which means if we compare 79 to hydrogen number 1, this actually, 79 is pretty complicated. It means it has 79 protons in its center, 79 protons, and that has 1 proton. My point is, and what it says on the slide, is that at the time the universe became an entity with regard to its own space and its own time that was going to expand and continues to expand, actually its expansion is accelerating. At that time there was only hydrogen, well, mostly hydrogen, okay, some helium, it's like I think, a 3-to-1 relationship between hydrogen and helium early on. Just a smidgen of lithium and then beryllium. So it stops at number 4 protons. And if you look on this, you're like, dude, we count on these things. Potassium, 19, where did they come from? Well, that came from stars living their lives. Okay, one of the things we're going to talk about, all stars, is they live their lives. They kind of, it's almost like a heartbeat in their center. Okay, they have nuclear fusion going on in their center, where they're making heavier and heavier stuff. Okay, and there's some limitation to how heavy stuff a star can make in its core. And other stuff was made by what we call nucleosynthesis. When the massive stars blow up, things kind of matter trips on itself, trying to get out of the way of the explosion, and it basically provides conditions for nucleosynthesis for some of this heavier stuff. So all of that stuff that we have here on Earth, it wasn't there 13.6 billion years ago. It took 13.6, well, it took some time for stars to live their lives, die, okay, and then new stars are born, live their lives, die. New stars are born, many generations to get what we love. Galactic cycling, we are made of stars. Okay, so this slide might help you explain that one. Okay. So this is a cool one. I don't know if you've been exposed to this, but this is neat. Your textbook kind of talks you through it. I know it's hard to see because the slide's really small. Okay? But if you focus on this up here, it's a classic. Basically, the Big Bang about 13.6 billion years ago. That is January 1st, right at midnight. Okay? So, like, you know, if you're like the geek that, well, it's not really geeky. You know, the party person who wants to stay up till midnight, whether there's something to do or not, right? Okay, so right at 12:01. Okay. So, and then actually right New Year's Eve, December 31st, 11:59. Okay, that time is basically 13.6 billion years. Okay, that's how this works. So with that in mind, notice that in February, that is when our Milky Way becomes an entity. Okay, so it takes a month. But then the next thing on the calendar is clear in September. In September 3rd, the Earth forms as an entity around our star. Okay, actually, we say the Earth formed. All of the planets in our solar system kind of formed through this kind of snowballing process we'll talk about. At the same time, we say that they were complete when the sun kind of turned on and kind of cleared the nebula. So the Earth became an entity September 3rd. September 22nd, okay, early life on Earth. Okay, so that's in September. The next thing on our calendar is clear until the month of December. Okay, and the month of December was a very busy month. So in the month of December, okay, not till the 17th day of December do we have the Cambrian explosion. Okay, 9 days later, rise of the dinosaurs. 4 days later, dinosaurs die. Okay, that brings us up to December 30th. Okay, so here, this would be what, New Year's Eve? December 31st? Like, what happened then? Well, at 9 p.m., early hominids evolve. Okay. At 2 minutes till midnight, 11:58, from modern hominids, early humans evolved. Modern humans evolved. If you are at are you right on the cusp of New Year's night, New Year's morning? 25 seconds ago, agriculture arises. 11 seconds ago, the pyramids were built. Okay, I know, you're like, wow. So that kind of puts the time span in perspective. So the last topic we need to talk about in this chapter is the thing that we are all in motion. Okay? It's kind of funny because I think of a little kid squirming, you know, a toddler, and you're like, dude, can you not sit still? No, you can't. So there's an assortment of motions. We'll be talking more about all of these motions later. But the first motion is the Earth spinning on its axis of rotation. And so in here, if I ever drag out, I was carrying this and was like, are you going to hit somebody with that? I'm like, no. If I drag this out, this actually is Earth's axis of rotation. Okay, so the Earth spins on its axis of rotation once every 24 hours. Okay, so, but one of the things that's interesting, and I hadn't thought much about it, but if you are at the North Pole, okay, and it's spinning, you're not moving as much as if you're at the equator and it's spinning. Okay, so actually we have speeds here, 1,670 kilometers per hour versus nothing. Okay, so I think that's kind of interesting. Earth rotates. The Earth also orbits the Sun. Now, I have some kind of important things on this slide. So, well, let's use this as the Sun this semester. Okay, so the Earth spins once every 24 hours. And if this is the Sun, right? And that is, what's the clock? Polaris, North Star, very good. So what happens is, can you see where instead of being up and down, straight, like 90-degree angle, I'm going to tilt it 23.5 degrees. So if you're an angles person, that angle right there is 23.5 degrees. It's supposed to be. Okay. So here's the deal. And it's all about counterclockwise, so I have to concentrate. So I'm going to go this way, counterclockwise. So here we go. This is the Earth orbiting the Sun. Okay. And I'm trying to kind of keep this, I know Polaris is there, but I'm trying to kind of keep this at a tilt 23.5 degrees. Okay, so it does that once a year. So that's another motion. Before I leave this slide, though, can you see down here I have an important term called the ecliptic plane, or plane of the ecliptic, sometimes it's called. Plane of ecliptic. And it actually is a player, the plane of the ecliptic. So I actually kind of, I don't know, like as I draw, this is the plane of the ecliptic, okay? I was going to say that the floor is the plane of the ecliptic, but that won't work because it doesn't really, yeah, the table's about the plane of the ecliptic, yeah. Does that make sense? It's the plane of the ecliptic. The cool thing is actually well, there's a lot of cool things, but if you are, let's see, observing, if you're out there, and you don't have to be like a mad scientist to observe. You know, if you just look up at the sky and you just think it's pretty, you know, that you are observing, right? If you're observing, a lot of times people will say, fine planets are on the ecliptic. And it's the same ecliptic. So like, here we go, this is us, right? Let's see, what's the planet that is one in from us? Venus, very good. So actually Venus is also on the same plane. What's the planet that's one out from us? Mars. I almost said Jupiter. You're right, Mars. Very good. They are all on the same plane, okay? And we'll talk more about why this is, but that means that if we're going to see them in the nighttime sky, they're going to be on this line called the ecliptic. All right. There's a lot on that slide. So motion, two types of motion we talked about. Okay, we talked about Earth spinning on its axis, rotating, and Earth orbiting the Sun. We call that revolving. Wait, yeah. Another sort of motion then exits our solar system and looks at the Milky Way galaxy. So our star is a member of the Milky Way galaxy, and so our star is moving around the Milky Way galaxy. One of the things we know about physics is if it weren't moving, it would basically just fall inward. That's not going to be a good thing, right? So it is moving, along with the other stars. You can see that it takes about 230 million years to complete one cycle around the Milky Way galaxy. Okay. And actually a second sort of motion is shown here. You see here this little box with the Sun, okay, And then you see kind of its nearby stars that kind of have different arrows. So there's a little bit of bobbing up and down in addition to moving. So that's just kind of two motions, right? All right. So that motion I said, now this isn't a motion, this is a separate slide. This isn't talking about motion, but this is important. Newton's laws that we're going to talk about in Unit 2 actually say if you observe this motion, you know something about the mass, how mass is distributed. If you just look at this motion, you can apply formulas, and we're not going to do them in here. But you can understand where the mass is. That's very important. So, you know, scientists being what they are, observe motion of our star, motion of other stars in our Milky Way galaxy. And what they found is that even though, like the slide says, even though the stuff that's shiny, okay, is kind of located in the ecliptic, okay, the ecliptic, remember, oh wait, sorry, they're located in the disk area. Sorry, the ecliptic was solar system, this is the galaxy. So most of the glowing stars are there. Actually, we have this nice big glowing region here. This actually is called the bulge. And all galaxies have this. It's a central bulge. And it glows because there's stars there. That's great. I don't know if I mentioned this yet, but actually there is a black hole in the center of our galaxy. So that's got to bring some mass, right? But what scientists found is that actually there is a whole bunch of mass. See how I'm going to kind of go outside the disk? This region is called the halo region. Okay, so we have halo above the plane of the galaxy and a halo below the plane of the galaxy. What they found is up there in the halo region, there is lots of mass. The reason they know there's mass there is because the characteristic motion of the stars. So there's all this mass there that's not glowing. So of course what I'm referring to or alluding to is this lots of mass that's not glowing is dark matter. Dark matter matters. Okay, so there's lots of mass, lots of dark matter in the halo region. So, and that's just from the motion of the stars. I've kind of likened some of the, you know how you look at the motion and then you infer or use calculations to understand the mass. It's kind of like, indirectly, like if you're fishing, and which I haven't done it all this year, I can't believe that. If you're fishing and if you're bobber fishing, you know, you look for that little plastic thing to go. If it goes up and down, even though you can't see the fish, you're like, dude, there is so a fish down there. And you can even kind of know how hungry they are, or if they're on the hook or not. If your bobber starts being dragged, you're like, I think I got him. Okay? So you can't see the fish, but you know it's there because of what the fish is doing. So that's kind of like understanding the presence of dark matter in the halo region of our galaxy and other galaxies. So this is another motion. Okay? It's a classic. It is actually raisin bread, and I've never eaten raisin bread before. Have you? Oh, is it good? Dang, okay.
You can get like blueberry bread too. Blueberries are in it.
Blueberry?
Too.
I bet. Well, thank you.
Yeah, try it sometime. You're missing out.
I think I will.
You know more about the stars than you do bread.
Making me hungry. So in this whole raisin bread or blueberry bread analogy, what you need to do is look at the raisins and consider them as galaxies or a cluster of galaxies. Okay, a galaxy. So here's the deal. Just as, oh, I know what else. Think of the raisins as galaxies and think of kind of the filling part as kind of what I've been calling the fabric of space and time. I'll just put space, time. Okay, that's like the stuff that's in between the galaxies. Okay, so the raisins are galaxies. Galaxies. Okay. So here's the deal. If as you bake your raisin bread or blueberry bread, the fabric of space and time expands, and it kind of carries the raisins along with it for the ride. That's exactly what our universe has been doing ever since it unfolded some 13.6 billion years ago. It has been, the fabric of space and time has been getting larger and larger and larger, okay? And carrying along with it the galaxies. So one of the things we're going to talk about is that Edwin Hubble actually, he could look at galaxies, like several galaxies, nearby galaxies, intermediate galaxies, and faraway galaxies, and he saw that they are all moving away from our galaxy. Now you might think, well, that must mean that the Big Bang happened right here with us. But not necessarily. There's really no location for the Big Bang. Okay? But the thing is that the closer galaxies are moving at, I'm gonna go down to this table. The closer galaxies are moving at, they're moving faster than that, but they're moving about 2 centimeters per hour. Okay? The intermediate galaxies are moving faster. Okay? Because they're farther from us and more fabric of space and time / more bread part is expanding. Okay? The farthest away, which is number 3 here, actually has the fastest, what we call recessional velocity. Recessional means moving away. Like if you have recessional after your wedding, it's the moving away part. Okay? So the farther away the raisin or the galaxy, the faster it's moving. And this actually, kind of in a nutshell, says that our universe is expanding. Okay, so we have that sort of thing. We'll talk more about that later. But to kind of summarize all that we've seen, okay, this is all the motions that we have going on here. We have the Earth spinning on its axis. Well, if you're at the poles, you're not moving, okay? We have the Earth orbiting the sun, okay? We have our star moving within the Milky Way galaxy, orbiting the center of the galaxy. We have a little bit of random motion with star kind of up and down the Milky Way galaxy. And then that last one says we actually, well, these last two, we actually have the Milky Way kind of moving within its local group and then the universe expanding. Okay, so I don't think I had a slide now that I think about it. This one right here, okay, I didn't really have a slide for that, but I did for the last one. When we were talking about Andromeda, didn't we? I think we did talk about the fact that Andromeda galaxy is in the local group, the Milky Way galaxy is in the local group, and they're doing this dance. Yeah, so that would be kind of that one right there. But even though they're coming together, you know, all galaxies, galaxies in general, are moving away from us, except for that one. Okay. Any questions about that? So we're going to go on and get a few slides under about for Chapter 2. So Chapter 1 assignment will be due on Wednesday. Yep. All right. Okay, so how are we doing? Yeah, I didn't print off 2. I know, you'll just have to fake it and buy the purple book. I don't think I brought any. There won't be very many slides to fill in. So. Okay, so what you're looking at here, there are all sorts of structures that have been man-made to kind of emphasize what's going on in the sky. Okay, so for instance, what I just had. So this is actually kind of centered on. Does it look like a bullseye to you? Yeah. This, I believe, would be in the southern hemisphere, and actually, as the Earth spins, you can create, if you know how to do it with your camera. What you do with your camera is to open up the shutter, and you have to kind of have a nice, some sort of lens that's nice and fast and kind of, but you open up your shutter, and as the Earth rotates, spins on its axis, the stars will appear to kind of spin around a particular location. That particular location for us in the northern hemisphere is around Polaris. So if I were to take a time-lapse photo of the North Star, and it's about counterclockwise, so I would see actually stars kind of whipping around it like this. Okay? Which, if I take my hand and do that, okay, so what do we say? That's east, right? That's east, and that's west, okay? If I go counterclockwise, make a bigger and bigger circle, look what I've done. I rise in the east and set in the west. So the reason for these star trails is the same reason the Earth spinning on its axis that we see the sun appear to rise in the east and set in the west. Okay, it's the same phenomenon. Okay. So this chapter is one of the things it does is just kind of, what do you see when you look up the nighttime sky? I could have asked you ahead of time, but you see stars. You might see something called the Milky Way, and we'll be talking more about that. The stars appear to be nice and like make pictures. Like, remember I gave you that constellation map for August? Okay. The planets, on the other hand, actually the word planets comes from, I think it's Latin for wanderer. The planets tend to wander against the fixed background stars. So the planets will wander. You might see this faint band called the Milky Way. And I have a picture here to show you what is the Milky Way. It will go from horizon to horizon. So constellations. Constellations are a picture. You know, sometimes we probably don't see the picture, okay, of things in the nighttime sky. Different, as you might imagine, different cultures have different sets of constellations. A lot of times our constellations for modern day have come from like Greek mythology. There's some wonderful stories that can be told about how the constellations interact with each other. On this figure, a few things. I bet you guys can see kind of these faint sort of kind of boxy sort of things. Okay, those are boundaries. It's supposed to be like a red line, but those are the boundaries. So for instance, let's see. All of these stars in this boundary would be part of the constellation Canis Minor. That's how that works. The star, a star we talked about the other day, remember the star Sirius? Seriously? It was like 8.8 or something light years away. Okay, and it is in the constellation Canis Major. Of course, everybody loves Orion. Who doesn't love Orion? As it turns out, there are 88 constellations modern day. Okay. I guess that's almost it. One last thing I see on this slide is, notice in green here, I'm tracing out something called the winter triangle. The winter triangle actually is not up right now, but the winter triangle is got 3 stars, and these are 3 stars in different constellations. So we have Betelgeuse in Orion, Canis Minor in, Procyon in Canis Minor, and Sirius in Canis Major. Okay. Ignore the Thursday if you want to. So let's take a look at these right quick. Different times of the year we'll see different constellations, and we'll talk more about that on Wednesday. Okay. But if you're trying to kind of learn a little bit about constellations, this is a good place to start. What I've circled in green up there is the Big Dipper. It's a set of stars. It just makes me smile when I see it. If I'm away from home, I'm like, well, okay, where's the Big Dipper? Okay, everything's right with the world. The thing about the Big Dipper is it kind of help orient yourself to the sky once you've found it. Sometimes the Big Dipper, let's see, right now the Big Dipper is kind of here, maybe, I don't know, 5 degrees or so. It seems like it's pretty low. Sometimes the Big Dipper is high in the sky. What star is that? Polaris? we're going to see that actually the Big Dipper throughout the year at the same time of the evening, the Big Dipper moves counterclockwise around Polaris. So sometimes it's low, sometimes it's high. Big Dipper. But the Big Dipper helps you orient yourself, because if you look at, these are called the bowl, that's the bowl, and of course that's the handle of the Big Dipper. Okay, so if you focus on the bowl, if you look at these two far bowl stars, if you go up, okay, they can help you find Polaris. Okay, actually they're called pointer stars. Okay, let's see. The other thing about the Big Dipper is it can help you find another bright star. You can take the handle and you can arc the handle to the star called Arcturus. It's in the constellation Bootes, which makes me laugh. Okay, let's turn our attention to this one over here. We had the winter triangle on the previous slide, and here, actually, this is up right now. We should be able to find the summer triangle. Summer triangle. And the summer triangle, like the winter triangle, is 3 stars and 3 different constellations. I think it's kind of pretty to see this constellation right here. It's got 2 names. It's called the Northern Cross, but it's also called Cygnus the Swan. That's very distinctive. And this one, Delphinus, I love Delphinus. It is just the cutest little constellation. So let's go ahead. I think on Mondays, I'm going to start doing this. Here is Constellation of the Week. So yeah, we're done with your lecture. What I did for these constellations of the week is to just get some information off the internet and things I thought was interesting, so things I hope you find interesting.
Yeah, we've got one.
But I will also put it on. So let's take a look at this right quick, and I'll point out a few things. Notice what I gave you. It's got some cool stuff about, some students come and they're really interested in mythology. And they know more about it than I do, which isn't hard. One of the things I want you to know about this constellation is that actually the Big Dipper, can you kind of see the Big Dipper right here that we just looked at? It is an asterism, and that's not a bad word, okay? So I want you to know that an asterism actually is just a subset of a larger constellation. So asterism is spelled A-S-T-E-R-I-S-M. It is an asterism. Okay? And the whole constellation is a fair bit larger than the asterism, the Big Dipper. So the Big Dipper lies in the constellation Ursa Major, Big Bear. And if you kind of read the background of the mythology, it will talk about how a god, I can't remember which one, it's in here, but basically took a bear, a normal bear, and swung it by its tail and threw it. They do a lot of that. And threw it up into the stars to become a constellation, or into the sky to become a constellation. And that's why, because bears usually don't have a tail, but this one does. The handle of the Big Dipper is the tail of Ursa Major. So the other thing is, let me go ahead and circle. Do you guys see in the handle of the Big Dipper, the tail of the bear, is Mizar? Okay. Actually, Mizar is a double. It's an optical double. Double meaning there's a second star there. And a lot of times, even with naked eye, you can see a second star. It's called, I think it's Alcor and Mizar. So actually, there's 2 stars there. Okay, well, very good. I'll see you on Wednesday. So yeah, grab a pair of binoculars and it's beautiful viewing. If you have any questions, let me know.